but the momentum of the system would be conserved. Discern if momentum is conserved or not. Use momentum vector diagrams, and also use conservation of momentum to figure out missing measurements. So you went through all that in the pre-quiz. Give that one a shot. Have a conversation. Tell them why or why not. Okay, correct answer is yes, A. Here's a conversation that you should have had in your brain or with your neighbor. So looking at these forces, you're asking yourself, okay, are these external or internal forces? Okay, is gravity an external or internal force? External force. What object is that from? The Earth. Is the Earth part of the system? No. So external force. Notice, real quick, that this is a different question than conservation of mechanical energy. Okay, it's a completely different animal. Okay, conservation of mechanical energy said, hey, is there any non-conservative forces doing work? Okay, gravity is a conservative force. We're not asking conservative, non-conservative. We're asking external versus internal. Okay, so gravity is an external force. Normal force. Bless you. So what force? Sorry, what object is causing normal force? The ground. Is the ground part of the system? No. Like, uh-oh. We have two external forces, but do they cancel each other out? Yes, they balance each other. So the momentum of the system is conserved if there's no unbalanced external forces. These are external, but they're balanced. So we're good. The consequence to that is that puck continues to slide at a constant velocity. Momentum is conserved. That is the evidence, but the reason is there's no unbalanced external forces. Good? Have a conversation. Correct answer is, bless you, if only one player is in the system, So gravity, normal force, they are canceling each other out, but the applied force is an external force that's not balanced. Momentum is not conserved. The evidence of that is, I mean, this is just like the bowling ball, bowling pin, just moving in some way, and then it's like all of a sudden moves in another way. Momentum is not conserved. But if we include both objects, both players in the system, same interaction, tell your neighbor, tell them why or why not. Correct answer is yes. So these forces acting on the other player, so gravity, and this normal force, those two cancel each other out. We're fine with that. This applied force, where did it come from? Came from this player who's inside the system. So now therefore this is now a internal force. This force, where'd that come from? From this player who's inside the system. So now this becomes an internal force as well. So yes, momentum is conserved of that system. So do you see how important it is to define your system correctly? You can have a scenario where it's like, oh, momentum is not conserved. Same scenario, yes, momentum is conserved. All based upon what you put in the system and what you don't put in the system. Good with that? Tell your neighbor why you think so. Correct answer is no. Momentum is not conserved. Friction. Okay, listen. Do not like, oh, friction. That's like a non-conservative force. Like, don't say that. That's for mechanical energy. Okay, friction is an unbalanced. Sorry, blah, blah, blah. Yeah, unbalanced external force. Okay. Consequence of that is you see the player moving, and then all of a sudden the player stopped. Momentum changed. Okay. Have a conversation.
Yeah, because they found some. No. How can it be both?
What do you say? If you sent the stick sliding across the ice and then it hit the puck, yes, momentum would be conserved of the system of the hockey stick and puck. However, the player is holding the stick, exerting an external force on the stick. Now, the force of collision between the puck and the stick, yes, that's an internal force, but there's other forces going on objects in the system, namely the guy pushing on the stick. So momentum is not conserved. How could you redefine the system so the momentum would be conserved? But the person inside the system as well, assuming no friction. You okay with that? And now that external force now is an internal force because the object that created that force is inside the system.
So what if you followed through the shot? Like with that stick not conserved?
Correct. If it's defined as the puck and the stick, still not conserved. If you consider it the player, stick, and puck, then it is conserved. Follow through or no follow through. Good with that? Tell your neighbor. Correct answer is? Correct answer is B, no. Momentum is not conserved. Okay? Mechanical energy is conserved, but we are not talking about mechanical energy. Okay? So gravity would be an external force that is not canceled out. The evidence of that, you could look at the puck and say, aha, yes, momentum's not conserved because I see it doing what? Dropping, specifically speeding up. It's accelerating, 9.8 meters per second squared. Momentum is not constant. Good with that? But if we have the same scenario, but now we include the Earth as part of the system, if we include Earth as part of the system, is gravity now an internal or external force? Internal force. Okay? Momentum would be conserved. Let me give you a practical piece of advice here. If you ever find yourself in a problem needing to include Earth in your system to get momentum to be conserved, figure out a different way to solve the problem. That's just ridiculous. You're trying to figure out how fast the Earth is moving up towards the puck. Like, that's just dumb. So in concept, this is valid. In practicality, find something else. Good with that? Okay. All right. So this is a subtle point, but an important point. Momentum has direction. So if momentum is conserved, then the direction of that momentum is also conserved. This is a difference in mechanical energy. Mechanical energy, when it was conserved, it doesn't have direction. It was a scalar. It had plus and negative and plus and minus, but that had to do with like gaining or losing. It had to do with like, are you in debt or out of debt? Okay. Just like temperature has positive and negatives. You're above or below zero. But it doesn't have direction. Momentum has direction. The math in this unit is easy. But this is where you're going to get tripped up. This point here. Okay. Direction matters. Like a ton. Okay. I'm going to start you out easy. I'm going to revisit the bowling ball, bowling pin collision. Both objects are in your system. Is everybody okay with A to the right? Okay. Afterwards, the total momentum still has to be to the right. Momentum was conserved. Good with that? Has to be conserved. Tell your neighbor what you think. Okay, correct answer is A. Now, I'm going to use this next slide. These are momentum vector diagrams. Okay. You won't necessarily, like, I'm starting out easy. You didn't necessarily need to use a momentum vector diagram to figure this out. I mean, you did. You just found out the correct answer is A without this technique. I'm just using this as a stage to show you what I'm talking about. Okay. So, objects in the system, ball and pin. The momentum of the ball beforehand was 20 to the right. The pin had 0. So the total momentum of the system is the ball's momentum plus the pin's momentum gives you 20 to the right. We figured out, hey, momentum is conserved so that the total momentum of the system is still 20 to the right. And then we're going to like back this up. 20 to the right is total momentum of the system. I had 15 to the right. 15 to the right plus something has to give you 20 to the right. What is that something? Well, that something's 5 to the right. Good with that? Okay. This is a similar tool to the bar graphs with working energy. This is the momentum form of that. Bar graphs don't work with direction though. Okay. Tell your neighbor. Correct answer is? Correct answer is B. Okay. Here would be the momentum diagram. You got 200 to the left. We'll call that negative. Okay. 140 to the right. Total momentum of the system is 60 to the left. Okay. Total momentum is conserved. So 60 to the right. Now, this was brought up in previous classes. They're like, well, isn't there friction? I mean, in this scenario, isn't that like a external force? It's not being balanced. It's true. So momentum's not conserved. Like, well, here's the deal. During the moments of impact, the force from the collision is so much bigger than the force of friction that we can like kind of ignore that for the moments of impact. They actually do this with crash scenes, trying to reconstruct it. They assume momentum is conserved during the moments of impact because the force from the impact completely dwarfs the forces of friction. I mean, there's friction all over the place. People are skidding like, but you can accurately reconstruct a crash scene assuming momentum is conserved simply because the forces of impact are so much bigger than the force of friction. And we're going to do that same approximation for here. You all right with that? Okay. All right. Typically, I do this demonstration, but I don't think my doctor would appreciate it. So, the scenario is this. The system is going to be the ball, person, and skateboard. Okay. And it's a medicine ball, so it's pretty beefy. Okay. Throw the medicine ball. Okay. So the question is, Okay, let me throw out this quick detail here. As they throw it, the ball is going down. It's affected by gravity. Okay, so momentum is a vector. Remember how, like with velocity, projectile motion, acceleration, projectile motion, forces, that the x direction is independent of the y direction. Okay, in the y direction, momentum is not conserved. The ball is falling down. But in the x direction, there are no. We don't have. In the y direction, we don't have. Sorry, in the x direction, we don't have to worry about gravity. So momentum can be conserved in one direction and not conserved in another. That's why I'm asking. In the horizontal direction. Okay. Go ahead and tell your neighbor.
So it doesn't say how much momentum that you can.
True.
Well, yeah, everything starts at red. But that doesn't mean that.
Correct answer is Y. Okay. Beforehand, there's no momentum. Afterwards, does the ball have momentum? Did the person on a skateboard have momentum? Yeah, both of them had momentum. They're moving. They have mass. How is it are you saying the total momentum of the system is still zero? They're going in opposite directions. Okay. Direction matters. So correct answer is B and C. So D. Okay. So here, 0, 0, 0, 0. I'm making this up. 15 to the left, 15 to the right. Add those up. That still equals 0. Total momentum of the system is still 0. Okay? I would recommend doing a momentum vector diagram on this one. Tell your neighbor. Correct answer is We're going to find out. So that explosion is an internal force. Okay. So they didn't really give us information about the individuals, but together there's 40,000 going up. That internal force of the explosion, momentum is still conserved. Bless you. Yep. 40,000 going up. Afterwards, they said it was 50,000 going up. So 50,000 plus something is equal to 40,000 up. Has to be 10,000 down. Does that make sense? You see why the vector diagrams, like the direction, is important. Okay? So, B. Okay. On this question, I would highly recommend drawing your momentum diagrams. Watch me. Have a conversation. Correct answer is? Here we go. Here's my prediction. Everybody who did this momentum vector diagram got it right, and everybody who didn't got it wrong. That's my prediction. So, initially, you have one to the right. Bowling ball has nothing. Total momentum of the system is one to the right. Total momentum of the system just in the horizontal direction. I'm not worried about the vertical, just in the horizontal. is still 1 to the right. Okay? Now, it doesn't tell us how much momentum the golf ball had, but it's moving to the left. Let's make up a value. It's not going to be more than 1. Does that make sense? I mean, ideally it would be like 1, but we'll just say 0.8 just for kicks and giggles. Going to the left, though. This plus something has to give you 1 to the right. That plus something will be 1.8 to the right. More than 1. What? Is that possible? Yep. Okay, first off, I'm not saying the bowling ball is moving faster than the golf ball. Okay? It's mass times velocity. Okay? So let's clear that off the board. But the total momentum of the system is to the right. So if you have something going to the left, the thing moving to the right has to compensate for that leftward momentum to make up so the total momentum of the system is still to the right. Does that make sense? This is like this slide here. The direction of the total momentum of the system is conserved. This is where this really like whoa, this is really important detail. Good with that? Your worksheet tonight is going to adjust this stuff due tomorrow. Yep.